In many cases, it is extremely difficult or even impossible to evaluate an improper integral. Using the comparison theorem and a carefully chosen integral, we can work around this to determine whether or not the integral converges or diverges. There are two parts to the comparison theorem. We have one case for divergence and one case for convergence. The first case deals with divergence. To use the comparison test, we need to check to make sure some conditions are met. We need to have two continuous functions over the interval a to positive infinity, f of x and g of x, that satisfy the inequality 0 is less than or equal to f of x, which is less than or equal to g of x. This needs to be true for any x we choose that is greater than or equal to a. Once we check that these conditions are met, we can use the comparison test. For the first case, if we have the integral from a to positive infinity of f of x dx, that is equal to the limit as t approaches positive infinity of the integral from a to t of f of x dx, and that limit is equal to positive infinity, we can then say that the integral from a to positive infinity of g of x dx is equal to the limit as t approaches positive infinity of the integral from a to t of g of x dx, which also equals positive infinity. This means that if the area of the region below the curve f of x over the interval from a to positive infinity is infinite, we can say the same thing about the area under the curve g of x over the same interval. This is because we know g of x to be greater than f of x. The second part of the comparison test deals with convergence. We have the same conditions as before, but this time we will consider the cases in which the limit is some real number L. So, if we have the integral from a to positive infinity of g of x dx is equal to the limit as t approaches positive infinity of the integral from a to t of g of x dx equals L, then we can say that the integral from a to positive infinity of f of x dx equals the limit as t approaches positive infinity of the integral from a to t of f of x dx, which equals m. In this case, we also have the condition that m is less than or equal to L. Let's try an example using the comparison test. We are given the integral from 1 to positive infinity of the function 1 over 3x squared dx, and we are asked to show that it converges. So our function f of x is 1 over 3x squared. We need to carefully pick g of x so that g of x is greater than f of x for all x. Let's choose g of x to be 1 over x squared. We can see that g of x will be greater than f of x for any x value we choose that is greater than or equal to 1. So, by the comparison theorem, if the integral from 1 to positive infinity of 1 over x squared dx converges, then so does the integral from 1 to positive infinity of 1 over 3x squared dx. Now let's rewrite the integral of g of x dx as a limit. We have the integral from 1 to infinity of 1 over x squared dx equals the limit as t approaches positive infinity of the integral from 1 to t of 1 over x squared dx. Evaluating the integral from 1 to t, we get the limit as t approaches positive infinity of negative 1 over t plus 1. Plugging in infinity for t, we get that the limit as t approaches positive infinity of negative 1 over t plus 1 is equal to 1. By the comparison theorem, since the integral from 1 to infinity of g of x dx converges, so does the limit from 1 to infinity of f of x dx. Therefore, we have proven that the integral from 1 to infinity of 1 over 3x squared dx converges.